We are the students of ComSat's University Islamabad WA campus. We are final year students of electrical engineering. I'm Ali Saad, and my fellow group member is Nismat Abid. Today we are here to present our final year project under the supervision of our hardworking professor, Ma'am Maliha Amjad. Our project title is AI-Driven Energy Optimization Balancing Solar and Utility Power. This is a home connected to renewable energy sources, solar panels, utility grid, and a battery for seamless energy storage. Sensors monitor voltage, current, temperature, and humidity, transmitting crucial data into our Raspberry Pi system. The Raspberry Pi runs AI algorithms like SVM and decision trees, processing data to choose the best energy source. Using smart switching, the system dynamically adjusts power flow between solar and grid based on calculated optimum. Enjoy the benefits of cost savings, eco-friendliness, and reliable energy supply as you optimize your energy sources. The motivation behind this project lies in the growing need for smart, cost-effective energy solutions. While solar energy is clean and renewable, it's often limited by weather and time. Purpose: this project introduces an AI-powered system that intelligently balances between solar and utility power. By predicting solar availability and monitoring real-time demand, it helps reduce electricity bills, improve solar usage, and promote sustainable energy management. Challenges: balancing solar and utility power is challenging due to solar intermittency and fluctuating prices, with manual switching causing inefficiency and waste. Irregularity of solar power. Solar energy depends on sunlight, making it unpredictable. When insufficient, the system switches to utility power. Fluctuating utility rates. Utility rates vary by time of day, and relying on power during peak hours increases costs. Energy management complexity. Manual or semi-automatic balancing of solar and utility power causes inefficiencies, higher bills, and wasted solar energy. Possible solutions: manual switching between solar and utility power involves manually monitoring solar power availability and switching between power sources. This approach is inefficient and can lead to higher energy costs if not managed well. Basic rule-based automation. A simple controller switches between solar and utility power based on preset rules. Fails to account for factors like fluctuating energy demand or varying utility rates. Battery storage solution. Excess solar energy can be stored in batteries and used later when solar power isn't available. Helps bridge the gap between solar and utility power. AI-driven energy management system. Uses AI algorithms to predict solar power generation and energy demand. Dynamically controls the switch between solar, battery storage, if available, and utility power using real-time data. Solar panel converts sunlight into DC electricity. This energy is stored in a battery through a charge controller, which also protects the battery from overcharging. The battery stores solar energy and provides power when solar or utility sources are unavailable. The inverter converts the battery's DC output to AC for powering household loads. The system uses various sensors to monitor voltage, current, temperature, and WAPDA availability. A temperature sensor monitors ambient temperature, while an optocoupler detects the presence of AC utility power and provides electrical isolation. A DC, analog to digital converter, converts analog sensor data, like voltage or temperature, into digital signals so the Raspberry Pi can process them. Machine learning models such as decision tree, DTT, are used for solar energy forecasting, load prediction, and analyzing battery status. These models help decide whether to use solar or WAPDA based on data inputs. Raspberry Pi GPIO pins cannot directly drive relays due to current limitations. Therefore, a transistor-based relay driver circuit is used. MOSFETs amplify the control signals and handle power switching. Diodes protect the circuit from back EMF during relay switching. Pulse width modulation, PWM, is used to control charging and switching operations efficiently. LCD displays real-time information such as battery charging status, current power source, solar or WAPD, and other system states. The Raspberry Pi collects data from all sensors and uses trained AI models to make intelligent decisions about power source selection. If solar energy is available and the battery is sufficiently charged, the system switches to solar power. If solar is insufficient or the battery is low, it switches to WAPDA. The switching is done via a relay-based circuit that ensures a seamless transition between sources, so the load, fans, lights, devices, etc., remains uninterrupted. When the system is powered on, it begins monitoring the availability of both solar energy and the utility supply, WAPDA. The energy source selection is made dynamically based on their availability. Primary source, the WAPDA. If solar energy is not available and WAPDA is present, the system automatically connects to WAPDA to power the load. Fallback to battery. In the event that WAPDA is also unavailable and there is no solar input, the system intelligently shifts to the battery as a backup power source, ensuring continuous power supply. Solar as priority source. If WAPDA is unavailable and solar energy is present, the system switches to solar power. The solar panel powers the load directly or via battery, depending on the configuration. The switching between sources is managed by the Raspberry Pi through relay-based circuits, ensuring a seamless transition without interrupting the load. This intelligent source selection is based on real-time inputs from voltage, current, and utility detection sensors, providing reliability and energy efficiency.